Hi, in this third video for Waveform Generator we are going to look at the phase converters. Before we look at how they're used in the software, let's open up the manual and look at the page describing the throughput through an advanced waveform. You see here we begin with an input phase. That input phase is a value between 0 and 360 degrees. We put that into the first phase converter that might change the value, again to a value between 0 and 360 degrees. That changed value goes to the second phase converters, and then to the third, and then that converted phase goes into our waveform. In the next video we are going to look at the value converters that can change that value that comes from the waveform generator. But right now we are only going to look at the phase converters. In the software, all of these three phase converters default to linear. And the linear phase converter will simply output the same value that you input to it. So it remains unchanged. So even though it goes through all three of these before it goes to our waveform, it will not have been changed. Let's look at the first phase converter. It's called inverter, and that's because it will invert the phase. Right now you see the value rises up to 1, then down to -1, and then back to 0. When we invert it, you see instead we'll go to -1 to +1 and then back to 0. Normally at this point we would insert 0 degrees into the sign, but now we have inverted the phase, we are actually inputting 360 degrees. Likewise, at this point we would normally insert 90 degrees, but we're inserting 270 degrees. Here we insert 180 degrees, and we did that also before the inversion. Up here normally we would input 270 degrees, but we're inputting 90 degrees. And this last value we're inputting 0 degrees instead of 360 degrees. And that will just invert our waveform. When you choose this inverter, it will default to invert the full range from 0 to 360 degrees. But if you need to, you can dial in something else, for example, from 45 degrees to 135. Now only this range will be inverted to show the same as out over here. So that's basically what this inverter does. The next on the list is the compress, and you can see our sine have been compressed to only fill 70% of this waveform. And the way it works is these first 25% we insert the same value as this first value of the compressed waveform. So all of these will be the value of 0 degrees being fed to our sine. Then we have our full sine, and then the last 25% will be asking the sine function to give us the value from 360 degrees. And no matter which waveform you choose, it will be compressed to this area. What you can do is you can, besides change the size between 1% and 100%, you can also choose where it should be located. It defaults to being in the center, but you can also say to you want it in the left side or the right side. If you listen to this waveform, it will have no effect if you have saved this waveform with it in the center or the left or the right side. The difference is when you start to combine more than one waveform. For example, if you multiply two waveforms, you will get a different result. So that's why you can change the side. The next converter is the shift converter. Let's go back to the sine. It defaults to 0%, but you can scroll to negative value to push the cycle of the waveform to the left, or you can dial in a positive value to shifted to the right. You can get an interesting effect by multiplying a waveform with a shifted version of itself. You can do that using a compound waveform. The next is the analogish. One thing that makes analog synthesizers sound different than digital synthesizers is the imperfections. And here you can set up the phase to be imperfect. You can choose how much you will allow it to be imperfect. And you can choose here 300 different values. You have 2 steps with seed values from 1 to 100. And you have 3 steps, again with seed values from 0 to 100. And then lastly, with 4 steps and seed values from 1 to 100. And the way it works is it will split, now with 4 steps, it will split the entire phase into 4 segments. And these 4 segments, normally they will be precisely 25% of the full range. But now we allow them to shift in total 10 degrees. So if you look here, you can see it at this point, it had been shifted a little to the right. Down here, it's also a little to the right, but very close to where it should be. Here, it should normally be here, so this part have been shifted a little to the left. So by dialing in different seed values, you can see we slightly shift it differently. And here you can choose how much you want it to shift. For example, I only want it to shift in total 2.5%, or I want to make it extreme. And you can shift it a lot more. Normally, I would say less is more. So I would dial in value probably not greater than these 10%, but it depends what I want to achieve. So, for example, if you want to generate a wave table with many of the same waveform that have this analogous phase converter, you can add a little movement to the sound, so it's not statically that each cycle is exactly as the previous one. In the next video, going into the value converters, you will see that there is also an analogous value converter. This one will push the values left and right along the x-axis, but dialing in analogous value converter, you will also start to move in the y direction. Let's look at the next. It's the frequency multiplier. And as the name implies, we simply add more copies of the waveform by increasing. Here we have increased it by 2. Now we have 3 full signs. And we can dial in a fraction. For example, if we want 3.7 versions of the waveform, we can do that also. One thing worth mentioning is if you increase this, you will start to see patterns emerge. Here you can see a slide pattern. Here again. And going to the end. Here you see these school examples of Moyer patterns forming. This pattern you are seeing is not actually there. If we go back, you can see all of these signs have the full amplitude. None of them are less high than the previous or the next one. And this have to do with how the waveform are being drawn. But I don't think it will be a problem, because normally you should never have to go so high in the multiplier. But at least now you know, if you need more of the same waveform, you just dial in the frequency multiplier. Next, we have the folding phase converter. And what it will do is you have here the full cycle of the sine, which it will fold over to a more narrow version of itself that's mirrored. Here it defaults to 60%, but you can dial it as low as 15%. When you increase it, it will slightly grow until they have the same size. At this point where they have the same size, they'll start to fold into a new copy that will emerge here at the middle. So as you increase, you will see a new version coming alive. And again, when it's full like here, again a new version will form in the middle. And you get this effect. So this is how the folding phase converter is working. A shout out to Nick Bat. We can also do pulse width modulation. And it comes in two versions, one called soft edge and one called sharp edge. They work the same. Normally in a synthesizer you can only do PWM with pulse wave. But since we are affecting the phase, we can do it with all of the waveforms. So here you see it traditionally with a square or pulse. And as you saw before, we can do it to a sine also. As you can see, this edge we have here is what I call a soft edge. I try to make it a bit soft where it transitions from the left half to the right half. As a result, you can see the distance from here to here is less than the distance from here to here. So this part of the waveform is asymmetric. Likewise down here, it's more easy to see that the distance from here to here is more than from here to here. If we choose the sharp edge instead, you see this edge is a bit more sharp, hence the name. But you see this top part is perfectly symmetric and the same as this lower part. So that's the only difference between these PWM and PWM2. It's how they transition from one side to another. And you can simply change the values to push them to as far as you want them. Right now, it defaults to this fixed point being 180 degrees. And it's this point, normally it will be here in the middle. So what we are actually doing is we are taking this point and we are shifting it left or right. But instead of only choosing that point, we have different options. Now, choosing this one, we will shift this point and this point at the same time. And we will either shift them towards the center or further away from the center. Here we push them further away. And here we push them towards the center. Also, we can choose either this point or this point. For example, choosing 90 degrees, then it's this point we're shifting. And the rest of the waveform will simply follow. So this is how the PWM phase converter is working. As I said before, this one works exactly the same, except it's either this soft edge or sharp edge. This one, the point shift, is more or less working in the same way. But instead of choosing some fixed values, you can choose exactly which part of the phase it is you want to push. For example, if I go back to 145 here. Now it's not pushed, the 45% value will be at the 45% place. But we can choose this value here and push that left or right. And you can just change it. So you decide which part of the waveform it is you want to move. And here you decide where you want to move it to. So it's not PWM, but it's in the same family. The next one I called half pi expander. And as you might recall, a full phase 360 degrees is the same as 2 pi. 180 degrees is the same as pi. So half pi is here at 90 degrees. So what we will do is we will take the part of the waveform both here at 90 degrees and here at 270 degrees, and we will push them further away from this line and this line, or further together. Right now it's expanding, so it's pushing outside from these two lines. But we can change that, and we can gradually move it closer and closer together. And you can make this extreme also. So even though this is a sine, you can almost make it look like a saw, and you can almost make it look like a square. For example, choosing a triangle. You can also make that almost look like a sine and make it even sharper. And of course, different waveforms will produce different outputs. Choosing a saw and make it with, for example, 48 harmonics, you can get this effect. The next phase converter is working almost identical, but instead of working both at 90 degrees and 270 degrees at the same time, it would only work here in the middle at 180 degrees. So choosing the pi expander, we get this result instead. And if you want to, let's dial in a sine, for example, you can combine them so you both have a pi expander and a half pi expander. When you're using multiple converters at the same time, their order can be important. It depends what they do. In sometimes you get a different result if you change the order. Instead of you manually changing them, you can right click and say I want to swap converters 1 and 2, and you see here in this example you get a different result based on which is first of these two. And had we had a third one, you can swap the location of the second and the third. Let's dial in a sine again. Next we have the sample and hold. I'm sure most of you will know this one from your synthesizers. What we're doing is we are we are sampling the phase, and then we hold it for 5 degrees. So that means for these first 5 degrees of the phase, we keep inserting 0 degrees into the sine function. Then we shift to this value of 5 degrees, and then the next 5 degrees will keep inputting 5 degrees into the sine, and that will produce the stair-step waveform. As you can see, each of the steps have the same width, but they will have different height depending on the waveform. This last value we can use to dial in a glide phase. Here I have set the first hold range to 10 degrees, meaning we will hold the value for 10 degrees, but we can choose how much of this phase we would set aside to glide into the next value. It defaults to 0%, so it'll go straight from this one to the next. But we can dial in, for example, here 30%. It means for the first 70% of these 10 degrees, that means for the first 7 degrees, we will hold that value. And then for the last 30%, or for the last 10 degrees of these 10 degrees, 3 degrees of these 10 degrees, we will start to glide into the next value. So instead of having these steep steps, they, depending on the waveform, they'll be more sloped. So as I increase this value, you see that the size of the step will be smaller and the glide will be larger. And here at 95%, we will almost have lost that effect of the sample and hold. Let's look at the next, segment swap. Here we have split the waveform into an equal amount of segments, and then we swap each odd-even pair of segments. For example, here we have the first segment of our sine. It have been swapped with the second segment of our sine. Here we have the third segment of our sine, and that have been swapped with this fourth segment. So as we increase the segments, we get different results. And when we reach a certain point, we get this effect where we see these steps. And as we increase them, we almost get our sine back with this wobbling effects. Instead of swapping all the segments in odd-even pairs, we can instead swap them first-last pair. So here we have the first part of our sine that have been swapped with the last part of our sine. Here we have the second part of our sine, or the second segment, and that have been swapped with the second last segment. So as we increase them, we instead get this effects. And as you can see, it has, to a certain degree, it have inverted our sine compared to this one. So this is the segment swap phase converter. The last of the phase converters is a segment shuffle, and it is related to the segment swap. Instead of swapping the segments, we are shuffling them or randomizing them. And we can choose the number of segments, and we can choose between 100 different seed values that are fed into the randomizer. In this case, seed 1, here we see the first part of the sine, the second part of the sine, the third, and the fourth. However, if we dial in different seed values, we'll see different results. And especially with many segments, you can see different results. It can be hard to see this started out being a sine at this point. In the first recording of this video, I skipped 2 of the phase converters, so let's deal with that now. We also have this one called Exponential, and it simply turns the phase into an exponential scale. So we can push it to either side like this. Right now it sees the range as one big range, but we can split it up to 2 ranges. So we have the first 180 degrees of the phase and the last 180 degrees of the phase. And we get this effect instead. And we can shift them. Instead of the normal, we can have this one reversed. So now it will, when it pushes this part to the right, it will push this one to the left and vice versa. So instead we get this effect. It's a bit of the same effect that you get when you do the pi expander. But not entirely the same. It's still something different. The other phase converter I forgot was this one called expand contract. It will split the entire phase into multiple bands, and each band will consist of ranges that will either compress or expand, and you get this rippling effect. As you increase the bands, you see you have these small ripples that you can change the size of. So these were all of the phase converters. In the next video, I will go through the value converters.